Good afternoon to all of you. Hope all of you are doing well and you're safe. And all of you, please stay safe, right? Okay. So in today's class, what we'll learn about is we'll learn about what is hardware, we'll learn about what is software, and we'll learn about what is engineering. Now, to start with, you must have very often used this term software and hardware. Okay, but let us try to define it. Let us try to understand what it actually is all about. So, software and hardware, these are not simple terms. These are composite terms. So, for example, what we imply by that is these are not simple word. These are composite word composed of constituent words. For an example, software is composed of two different terms which are soft and ware. Likewise, hardware is composed of two different terms which are hard and ware, right? So now we need to create definition for three different terms, right? Okay, we need to understand three different terms. These are soft, hard, and ware. Now, soft in computer science is used to refer to logical existence of an entity. Now, it basically refers to an entity that logically exists. So, for an example, whenever you prepare for your examinations, what you do is you learn from a book that physically exists. You create a representation of the book in your brain cells, which are called as neurons. Okay, neurons which are similar to that of physical book, but it logically exists. Okay, right? Okay, in order to present it in the examination, right? Okay, so a book that is there on the table is something that is physical, and a book that is there in your brain cells this is something that is logical in nature, right? Now, likewise, hard is in computer science is used to refer to an entity that exists physically. So, for an example, a robotic arm is something that realizes a business, but it exists physically. A pen, a book, or table, or chair, all of these are physically existing entity with which what you do is you realize certain business, right? Now, likewise, where in management is used to refer to an article of commerce, something with which what you do is you do business. So now, if I want to define software, software is a logically existing article of commerce, right? So something that exists logically, but what you do is you do business with that. So a set of computer instruction that realize certain business is called a software, right? Again, hardware is a physically existing article of commerce. So, for an example, a robotic arm with which what you do is you perform operation in a manufacturing unit is a hardware, right? Okay? So that is the basic distinction between software and hardware. Now let us try to define the term engineering. Now engineering, it may be an art or a profession of building or engineering a product, right? Okay, what it should inculcate in it is an art or and a profession of acquiring. Now, why acquiring is because whenever you're engineering a product, what you need to do is you need to have a sufficient knowledge about what the product should look like, what the product should do, and what the product is expected to do in future, because you need to have adequate knowledge about what is to be built. So that's why this particular term acquiring is placed in here. So it is the art and profession of acquiring. So once you acquire knowledge, then what you need to do is you need to apply certain principles that are scientific in nature, right? Okay. Why scientific? Because it has to have certain organization. You should know what to do when or what to place where. So it has to abide by certain scientific principles, right? Okay. It has to abide by certain mathematical model. There has to be suitable structure given to an engineered product or engineering product, right? Okay, there has to be economic principles that apply to see the viability, right? There has to be social principles that has to be applied to see whether to see what kind of implications the engineering product has, right? Okay, so All of this may be scientific, mathematical, economical, social knowledge should be applied to design and build a system, right? Okay. System that should be capable of realizing the problem and building a suitable solution for it, that is which is the need of the society, because eventually what we do is we engineer a product for the benefit of the society. So engineering, if defined, has to inculcate or include all of these attributes, right? Now to move on, what is software engineering, right? Again, software engineering is a profession dedicated to designing, implementing, and modifying software so that it's of high quality, more affordable, maintainable, and faster to build, right? Definitely, um, mm, software engineering, whenever you're engineering a software, there has to be a mechanism for providing suitable design, a mechanism for implementation, right? A mechanism for modifying the software, right? Which exhibits very high quality. It should be more affordable. It should be maintainable and faster to build. And these are the attributes that qualify a software to be a very good software, right? So it is also defined. It also defined a systematic approach to analysis, right? Design, assessment, implementation, test, maintenance, and re-engineering of software by applying engineering principles to software. So whenever you are engineering a software, it is very important to analyze. It's very important to analyze the various entities, identify the attributes, they identify the behaviors and their relationship. It's very important to provide a suitable structure, right? It's very important to assess the ability or to test the system. It is very important to implement the system properly in the client's environment. Again, it's very important to have a very good strategy built in for maintenance, and there has to be a mechanism built in for using the software to design new system which may be of use in the future. Now there might be two different categories in which softwares may be a software product may be categorized. It may be system software or it may be application software. The basic distinction between these two is that system software is a software that enables interfacing between a software product and a hardware product. Best example for that is operating system. An operating system enables a hardware system and software system to interact with each other. For an example, device drivers that enables you to use your USB devices or enables you to port the USB devices to the computer system, right? Utility program. So these are the examples of system software. Whereas application software is a category of software that allows the user to accomplish certain purpose-specific output. So, for an example, stock management software, data processing software, database management system software. So, these system enables the users to achieve their own purpose-specific objectives. So these are called as application software. So a software system can be broadly classified, categorized into these two different categories: so the system software and application software, based on their utility. Now, this is a very well accepted definition of software engineering is standardized by IEEE. You must have come across this particular term, IEEE. IEEE stands for Institute of Electrical and Electronics Engineers. So they have standardized definition for software engineering, and the definition goes as software engineering is an application of systematic, disciplined, quantifiable approach to development, operation, and maintenance of software, and the study of these approaches, that is, application of engineering to software. Now, just see, what we'll try to do is we'll try to fragment this definition and we'll try to understand it, what it tries to imply. Now, software engineering is application of systematic. Now, systematic basically here infers to organized. Every engineering approach should have certain organization. That is, one should be capable of knowing the sequence in which the activities are to be executed in order to attain the solution or in order to attain the software. So it's software engineering should have a systematic approach, right? It should be well disciplined. Discipline here tries to infer to, or it tries to refer to, there has to be a mechanism for monitoring and controlling the progression of the software development, because until and unless you don't have a proper mechanism for monitoring and controlling the progression of software development, it may be very difficult for one to determine the completion or the point where the software system the time by which the software system should be actually developed. So, for an example, in software engineering, we have a problem that is called as 99% complete syndrome. 99% complete syndrome basically refers to a situation where the developer feels that the software system is nearing completion where it is actually far from completion, because there is no proper mechanism put in place for monitoring and controlling the progression of the software development. So here, by disciplined basically means we have to have a proper mechanism for monitoring the progression and the development of software system. Now, the approach has to be quantifiable. Quantifiable here basically tries to emphasize on the fact that uh, every software lifecycle phase, or every phase in software lifecycle, should have or should be able to deliver certain quantifiable results. By quantifiable, it means that it should generate certain measurable results, right? Okay? Results that can be used as the basis for determining the extent of work that's being done in the development of the software system. So every phase has to deliver certain quantifiable results that are measured to determine to what extent the project is over. So if there is a mechanism that is used that can be used to assess the results of the identified phases, then we can avoid the 99% complete syndrome that we have just been through. So it should be systematic, it should be disciplined, and it should be quantifiable, right? And these three approaches should be applied to development, operation, as well as maintenance of software system. Because in case of development, also what we need is an organized, controllable mechanism. Whereas in case of operation also and in case of maintenance also we require the same. So these three approaches should be applied to all the three phases of software lifecycle. That is development, operation, as well as maintenance, and study of all of these approaches, right? And a detailed study of all of these approaches and application, and that implies application of engineering to software. So what we need to have is we need to have a proper, organized, accessible, controllable mechanism for development, operation, and maintenance software system. So that is what this particular definition tries to inculcate in it. Now, coming back to the definition, coming back to the difference between software and hardware. Now, there are two curves. This is one of it. This is one of it. It tries to exhibit the difference in the behavior that is exhibited by hardware and software with respect to time. One of the factors that are taken, one of the factors that is taken into consideration for assessing the behavior that is exhibited is failure rate. Okay, right? Now, this is a very simple graph uh, in which across one of the dimensions across one of the dimension we have time, and across the other dimension we have a failure rate. Okay, so this is a qualitative representation where what we do not have is we don't have quantitative values, right? Now if you closely look onto this particular graph, there are two curves that are highlighted. One is called as idealized curve and the other one is called as actual curve. Okay, so it basically represents the curve that is ideally expected from the software system, and a curve that is actually exhibited by the software system with respect to time in terms of failure. Okay, right? So here I'll use the assistance of the mouse pointer try to point to different time frames. You see, initially a software system may exhibit a very high infancy mortality. Very true. A software system may exhibit very high infancy mortality because of the various reasons, out of which one of the reason may be a software product is or a software system is not capable of catering to customers' requirement. Very true. If the software system does not meet what the customer wants, then it may exhibit very high infancy mortality rate because software system may be rejected by the customer. So this it may be one of the reason. The second reason may be a software system is not capable of working in the client's environment. Very true, right? Because till now the software system was developed in the developer's environment, and post delivery it's placed in the client's environment, so it's not capable of adapting to client's environment. For an example, you buy the developer's environment has a quad core facility, whereas the customer's environment has only dual core facility. Then in such situation the software system cannot be used in the customer's environment. So this may also be one of the reasons why software system may exhibit very high infancy mortality. Right now, the third reason may be um, there might be a situation where there is a rival in the market that has built up a similar system with lesser cost compared to that of yours. Now, there is a business risk. So there is a rival that is ready to provide the customer with a product that is better than yours with a lesser cost. Okay. Now that may also be a reason. So a software may exhibit very high infancy mortality rate because of the first reason is that it's not capable of meeting up the customer's requirement. Second reason is that it's not capable of adapting to customers' environment. And the third reason may be there might be a business risk in the market that disables you to become a contender for the solution of the to be provided to the customer, right? So software system may exhibit very high infancy mortality rate because of these very reasons. Now anyhow, you have developed the software system, so what you need to do is you need to bring down this failure rate. So what you need to do is you need to invest effort, time and cost to bring down this failure rate to certain acceptable level. Now let us consider this is the point in time when the customer is ready to accept the product and it's put to use. So once the product has been accepted by the customer, then the product is expected, or the software system is expected to behave normally or for prolonged period of time, right? Again, it's expected to deliver all expected results for a prolonged period of time. Now this is called as idealized curve. This is what ideally is expected from the software system. Now let us see the actual curve, the way how software exhibits behavior. Actually, a software system exhibits very high infancy mortality rate. This may be because of the reasons that we have already identified. Maybe because of the reasons that we have already identified in case of the actual curve, idealized curve, right? So likewise, you need to bring down the failure rate to certain acceptable level, and the product is accepted by the customer and is being put to use. Now see, at this particular point in time, a change is called for. A change is called for it may be called for because of the various reasons. It may be called for either perfection, it may be called for either adaptation, it may be called for either perfection, or it may be called for either prevention. So it may be either corrective maintenance or perfective maintenance, or adaptive maintenance or preventive maintenance. But because of the change that is being introduced, you'll see that there is a spike in the there's a certain spike in the failure rate, because change in one of the module may result in other modules not being able to perform its functionalities, right? So there is a cascading effect in the modular orientation, and the other modules are not able of performing activity. So there is a spike in the failure rate. So again, what you need to do is you need to bring down the failure rate to certain acceptable level here, right? But you must have observed that the failure rate is considerably higher here. Why? Because any change that is brought about to the structure of the system makes the system much more vulnerable, right? I'll repeat it. Any change brought about to the structure of the system makes the system much more vulnerable. So here you'll see that the system has become much more unstable because of the structural transformation that is taking place. So likewise, it continues. So here also a change is being introduced. The failure rate spikes up, right? Again, what you need to do is you need to bring down the failure rate, right? So just see, as more and more changes are being introduced, continual structural transformation is being introduced to the software application, because of which the overall failure rating is increasing in nature. But it's not increasing abruptly, it is increasing gracefully. So that's called as that's the reason why it's said that a software system gracefully degrades with respect to time. It gracefully degrades with respect to time. That implies that although it's being used, because of the structural transformation, the failure rate increases. So this is the actual curve that is exhibited by a software system, our software system with respect to time. So you need to have a clear understanding about the idealized curve and the actual curve. Okay, right? Now let us try to understand a few laws of software evolution that is very much important in context to the behavior that is exhibited by the software system. Now the first law is the law of continuous change or continuing change. Now, this law says that a software system should continuously change during its lifetime, or it should become progressively less useful. Yes, because in order to increase the lifetime of the software system or the use time of the software system, a software system should undergo continuous change because it should adapt to new functional requirements that the customer wants the system to support. If the system is built in a very rigid manner that it's not capable of including new changes, then the software system will definitely fail. Okay. The second law, the law of increasing complexity. The law of increasing complexity basically tries to address to a situation that when changes are being introduced, structural transformation of the software takes place. And if structural transformation of the software takes place, then the software system becomes much more complex and vulnerable to failure. Okay, right, as we have discussed, whenever we were trying to understand the actual curve, when more and more structural transformation takes place, the structure of the software system tends to degrade and becomes much more vulnerable to failure. Now, law of conservation of organizational stability, it tries to address to the fact that prior to the deployment and post to the deployment, the rate of development should be approximately constant, right? So there should be almost equal amount of change being introduced prior to the delivery and post to the delivery of the software system. Okay, that means equal amount of work should be done during development phase as well as maintenance phase. Now, the fourth law is the law of conservation of familiarity. Now, law of conservation of familiarity basically tries to address to a point that whenever changes are introduced in the successive versions of the software system, it should be approximately constant. That means the successive versions of the software system should have some similarity to enhance familiarity, because only if the software system are similar, it becomes familiar to the user. For an example, the basic essence of a different operating system that Windows have released are almost same. Why? It's done so is just to maintain the similarity, to enhance familiarity. So that's it's very much important for you to understand that. So these are the four important laws that are there related to software evolution that you need to understand. So law of continuing change, law of increasing complexity, law of conservation of organizational stability, and law of conservation of familiarity. Now, likewise, let us try to understand the behavior that is exhibited by hardware with respect to time. Now, if you see here, the idealized curve is not expressed explicitly because it will be same as that of software. What I'm trying to infer by that is a hardware system exhibits very high infancy mortality rate, as similar to that of software. It may be because of the similar reason that the reasons that we have specified for software. There might be certain manufacturing fault in the hardware, right? Because of which the hardware is not capable of sustaining the application for which it's built, right? It may be because of the reason that the hardware is not capable of interfacing with the software with its build. You see, the first one is trying to focus on manufacturing fault, and the second one is trying to focus on the adaptability issue between software and hardware. And the third may be business risk, a situation where there is a competitor in the market which has manufactured hardware product similar to that of yours and with enhanced capability and lesser cost. Now, this may be the three very reasons why a hardware system may exhibit a very high infancy mortality. Now, once certain amount of cost investment is made in terms of effort, time, and cost, and the manufacturing faults are looked over, you need to bring down the failure. You need to bring down the failure rate to certain acceptable level. And once the failure rate has been brought down, now the hardware system is expected to behave normally for a prolonged period of time. But actually, if you see here, a hardware system exhibits very high late mortality. Late mortality means a hardware system may fail abruptly at a later point in time. Now, what may be the reason for this is a hardware system may exhibit a very high late mortality because of continuous wear and tear from the environment. So, for an example, if you continuously plug and unplug your hardware system, there might be a breakage which will further disable the hardware system to perform its expected activity, or there is a power outage because of which the hardware system fails to deliver the result. So a hardware system exhibits abrupt failure during use time because of the wear and tear from the environment. So this is the actual curve that is exhibited by the hardware with respect to time. Now, if you see, it also resembles the cross section of a bathtub. So that's the reason why it's also called as bathtub curve. Okay, so the nature of the curve that is exhibited by the hardware with respect to time is also bathtub in nature. So we'll stop here and we'll continue in the next class. Thank you very much.